Okay, YouTube, in this video we're going to work through the protocols for using the elimination method, which is our second major method for solving systems of especially linear equations in two variables in this particular case. But the elimination method is just that. We are going to use eliminations to our advantage to hopefully find some x and y that when we plug it into both of these equations satisfies the entire system. So I'll take you through the steps here, but the first thing I want to do before we actually use the steps to solve the system is just to say that we also refer to this as the linear combination method, because what we're basically going to be doing is this. We are going to, and I'll put a little addition bar down here, we're going to straight up add these two equations together. So I just want to point out that if I did this right now, if I did it, okay, because x and y satisfies both of these, x and y have the same values in each equation, it's totally fair to do this. I could say 2x plus negative 4x is negative 2x. And I could add my negative 3y and positive 2y to come out to be a negative 1y. And I could add my negative 1 and my negative 2 to get a negative 3. The reason why we refer to this as linear combinations is because we've combined these two lines. But we also call this elimination method because what would be really cool is if I were able to add these two equations together and I got my x's to, like, totally cancel out. Totally cancel out. Because if I were to leave just the y now, then I could get y by itself and say, well, now I know the y value. Let's go substitute that back in and find x. So I want to consider this question before we read the first step, but what would have to be true about the values of both of these x's right here, that if I added them together, they canceled out? And the idea is that they would have to be opposites of one another. They'd have to have the exact same coefficient value, but one would have to be positive and the other one had to be negative. So I'm going to get all of this writing out of the way here, and we'll read step one now that we've established this, but it says multiply one equation, or maybe both of the equations, by some constant. You get to choose the constant, but we want this constant to multiply them such that we obtain coefficients, or numbers in front of the variables, that differ only in sign, S-I-G-N, sign, for one of the variables. So for instance here, x. I noticed that if I were to say, take the first x here and double it, it would become a 4x. And if I add that now to my negative 4x, it would cancel out. So I think that that's probably the easiest possible route, because if I wanted my y's to cancel, I would say, well, the quickest multiple, or the least common multiple between those two things would be 6. I would have to make one of them a negative 6 and the other one a positive 6, which means I have to multiply both equations by a constant. Whereas in this case, what we're going to do is we're just going to pick this equation here, and we're going to multiply the whole thing by a 2. So what this means is when I distribute this through, this is important, you have to distribute it through the whole equation. You haven't changed its solutions. It'll have the same set of solutions, or the same graph. It's just that its values are different. And so I get this new system that is going to be 4x minus 6y, and that'll be equal to negative 2. And I'm going to rewrite the second equation because we didn't need to modify it at all. So here's where this elimination part comes in, and also the linear combination. When I add these lines up, I'm going to see that my x's cancel out. So negative 6y's and positive 2y's is negative 4y. And adding these together, I get negative 4 constants. So now you notice that we got one of our variables to be left, and we can get that isolated. So we say y has to be equal to 1. So the nice thing about this is we know part of our solution now. In terms of the solution to the system, we know that if there's a solution, and there is here, the y value has to be 1. And that being said, since this y value is a solution to either equation, what we're going to do now is just pick one of these equations to plug that y value back in and go solve for the x value. So given the fact that I'm going to be looking for x now, I kind of care to get this x by itself in the first equation because, well, it's a little bit smaller and it has a positive coefficient. It doesn't have a negative in front of it like negative 4x. But I'd have 2x minus 3 times our y value now is equal to negative 1. And when I put in this y value as 1 from right here, we can actually just go ahead and solve for x now. So we get 2x minus 3 equals negative 1. I also know that if I add 3 to both sides here, add 3, I'm going to get 2x is equal to 2, and it follows that dividing both of these by 2, I would say then x equals 1. Box it. Make sure you box it. But we say 1. So if I said now, what's the significance of this point right here? Well, if we were to go graph both of these equations, I guarantee you that they cross at 1, 1. As a matter of fact, I have the graph of both of these equations here, and it's very easy to see that they do indeed cross at each other at the point 1, 1, or they have that common solution right there, okay? So questions to consider before we tune out of this video is, looking at the original system, it said which variable in the original system was the most convenient to eliminate and why? Well, it was the x variable, and the reason why is because, Well, we only had to multiply the top equation by a 2 to get these to be opposites of one another, the 2x and the negative 4x to be opposites of one another. And then it says, does the graph of the system support our solution that we found? Well, the graph indeed does support the solution to the system. We can see that that is their one point of intersection. Cheers.